Next one, we are learning about 7.3. 7.3, thin lenses. First of all, we need to know that we have two types of lenses. First one is normal lens, and then another one is thin lenses. So normal lens is an optical system with two refracting surfaces, while thin lens is the simplest lens that have two spherical surfaces that is very close together, and we can neglect the thickness of the lens. So this is an example for a lens. This is a glass globe, and the glasses or spectacle is the example for thin lens. So we have two types of thin lenses. The first one is convex lens or converging lens, and another one is concave lens or diverging lens. So this is how the convex lens look like. You need to be symmetrical, left and right side. And different with mirror, this time we have two spherical surface, and that was imaginary, and in between the overlap surface is the lens, convex lens. So we have optical axis with focal point 1, focal point 2. So the length of the focal point must be equal, left and right. And we have twice the amount of focal length, left and right side as well. So for concave lens, this is how it looks like, and we must draw the dotted line at the center. And different with convex lens before, concave lens is two spherical surface with some distance at the center in between two surfaces. So the gap between them is the concave lens, and we draw the optical axis, and we also have the focal point 1, and then at the back focal point 2, and the distance between them is equal, and twice the amount of focal point 1 and focal point 2 need to be the same distance as well. So let's draw the ray diagram. So for the object distance is greater than 2f, let's say this is our object, and the first ray goes straight, and then you go through the focal point 2. So this is our first ray. And then for the second ray, so let's use orange, you go straight to the very center of the lens. You make sure you use your ruler until you get it right. And this is our second ray. And then for our third ray, you go straight to the focal point 1, and then when you see this the centered line, you go parallel line to the optical axis. So the intersecting three lines is where our image lies. So we get the image already. So this is our image. Right? So for concave lens, at any position of the object, it will produce the same image. So I put my object here, and then for our first ray, you must go straight to the center, and since this is diverging lens, so the ray must be diverged. Is it here, here, or here? It was somewhere. So same with mirror, we use our focal point as our reference. Okay, so we know the angle already. We just use ruler and we extrapolate behind the lens. So this is our first ray. And then the second ray, you go straight to the center, same with convex lens just now. Go straight to the center, and this is our second. And for the third ray, you go straight to the focal point 2, and we're not done yet. Since this is diverging lens, the next line we need to do it parallel with the optical axis. And last one, we need to extrapolate the third line behind the lens. Now we get our intersecting lines already. So this is our image. Now let's look at the characteristic from the image we get just now. So it was real behind the lens, and it was inverted, and it was diminished, which is smaller in size, and it formed at between the f2 and 2f2. For concave lens, the image is virtual since it was in the front of the lens. It was upright, diminished, small in size, and it was formed at the front of the lens. Well, actually we have 5 different cases for converging lens, same like mirror in 7.1. So the first case is when our object is greater than 2f. So object here, the first ray goes straight and converge at f2. Second ray goes straight to the center of this lens, and the intersecting rays is our image. And it was real, inverted, diminished, and formed in between f2 and 2f2 at the back of the lens. For second case, when our object is exactly on the 2f. So our object is on the 2f1, and then the first ray goes straight parallel with optical axis and converge at f2. Second ray goes straight to the center of the lens, and the intersecting rays is our image, which is real, inverted, same size, and formed at point 2f2. For our third ray, when our object is in between 2f1 and f1, so our object here, so first ray goes straight again and then converge at f2. Second ray goes straight to the center of the lens, and now we get our image here, which is real, inverted, magnified, and formed greater than 2 f2 at the back of the lens. For our fourth case, when our object distance is exactly on f1, so the first ray goes straight again and then converge at f2. Second ray goes straight to the center of the lens, and our image is real or virtual because two rays are parallel with each other and it forms an infinity. For the fifth case, when our object distance is less than our focal length, so the first ray goes straight and then converge at f2. Second ray goes straight to the center, and then we need to extrapolate until we get an image which is at the front of the mirror of the lens, and then it was virtual, upright, magnified, and formed at the front of the lens. So for diverging lens, we only have one case, because at any position of the object you will produce the same image. So let's say our object here, the first ray goes straight and it will diverge at f2 as our reference, and the second ray goes straight to the center of the lens, and the intersecting rays are our image. And the characteristic, it was virtual, upright, diminished, and it was formed at the front of the lens. So that's all for sketching. So let's do some maths. Okay, we're introducing you the thin lens equation. So this one is just the same like spherical mirror equations. 1 over f is equal to 1 over u plus 1 over v, where f is the focal length, u is object distance, v is image distance. So for magnification equation, m is equal to h image over height object is equal to negative image distance over object distance. This one also we have learned in mirror, yeah. And now for the sign convention, this one also the same like spherical mirror in 7.1. Okay, the only thing different with mirror is if we look closely at the focal length. So for mirror before, we learned that focal point positive sign is for concave mirror and negative for convex mirror, but this time the focal length for a convex lens is positive and focal length for concave lens is negative. So please be very careful with the sign convention when you want to do the calculation. So we have two equations already. So the final equations in 7.3 is Lensmaker's equation. So Lensmaker's equation states that 1 over f is equal to n2 over n1 minus 1 over r1 minus 1 over r2, where n2 is refractive index 2, n1 is refractive index 1, and r is radius of curvature 1, r2 radius of curvature 2. So this is our convex lens, and this is our concave lens. Now we have two surface, that means we have two radius of curvature. This is r1 and the other side is r2. And for convex mirror, the r1 is positive value and then r2 is negative. Meanwhile, for concave lens, we have r1 on the left and r2 on the right, and for r1 it was negative value r and then positive for r2. And if you wonder why we have some r is positive and some are negative, this is because we have a rule to determine the sign. Okay, so for convex surface, the radius of curvature is positive, and for concave it was negative, and if your lens are flat surface, the r is infinity. However, we are not learning just two types, but actually we have 6 types of lenses in total. So for convex lens, we have 3 cases. We have 3 types. First is biconvex that we learned just now, and then we also have plano-convex, and we have convex meniscus. Meanwhile, for concave lens, we also have 3 different types of lens. Okay, first is biconcave, we learned just now, and we have plano-concave, and we have concave meniscus. Now let's do some example. A person of height 1.75 meter is standing 2.5 meter in front of camera. The camera uses a thin biconvex lens of radius of curvature 7.69 mm. The lens made from the crown glass of refractive index 1.52. So A, calculate the focal length of the lens. So we have the height of object already, which is 1.75 meter, and then they told us that this is biconvex lens. And they also told us that the U is 2.5 meter in front of the camera, so our object distance is 2.5 meter, and the radius of curvature is 7.69 mm, so that was R, and the lens is made from N2 is 1.52, so our N1 is R, which is 1. Question A, calculate the focal length of the lens. So we cannot use the thin lens equations because we don't have the V. So we use the Lensmaker equation, and then we just substituting everything that we have. 1 over, okay, for radius of curvature, we need to determine whether the sign is positive or negative. So we learned before that convex surface is positive R and concave surface is negative R. So we use the same value but different sign. Be very careful with this. So R1 is positive and R2 is negative. Students also always make mistake for this, so be very careful, guys. 1 over minus again, and then you just press the calculator and then you will get the answer, which is 7.39 millimeter, the focal length. So that's it for A. And for B, sketch a label diagram, ray diagram to show the formation of the image. So first thing first, we draw the convex lens and the center. Next is the optical axis. And then we need to determine where is the focal point 1 and then twice the amount of focal point. Draw this first and then look where is our object. So our object is, our focal point is 7.39 and our object is 2.5. That means our U is greater than 2F. Okay, so our object must be greater than 2F. Put it here. And then our first ray goes straight and then converging at F2. And then our second ray goes straight to the center of the lens. Okay, so this is second, and then second as 2 rays is enough to get an image. So the intersecting lines is our image. Well, that's it. And for question C, determine the position of the image and its height. That means they want the V and the HI. So we use the thin lines equation. We have the focal point from A, we just substituting, and 1 over 2.5, 1 over V. So we want the V, so you press the calculator and you will get 7.41 millimeter. And for the height image, we use the magnification equation. So we have the V already, we have the HO, we have the U. Substitute everything in the equation. 7.5 minus 7.41 times 10 to the power of negative 3 over 2.5. And then we press our calculator. Then the final answer will be negative 5.19 millimeter. It was very, very small. And if you wonder why our height is negative, this is because the magnification that we get is negative, and that tells us that the image produced is inverted. And for question Z, we can simply get the answer from questions B from the label diagram. So it was real because the image produced in front of the it formed at the back of the lens, and then it was inverted because from C we get the magnification is negative, and it was diminished, which means it was smaller in size because the magnification is smaller than 1, or the height image is smaller than height object. And the image is formed in between the F2 and 2F2 at the back of the lens. Well, that's it for chapter 7. Thank you for watching. I hope you enjoy. I'm Najah Bakri. See you next time. Have a very nice day.